So this last little part here of section 2, I want to do just because I think it's really interesting and I find it cool. Section 3 is most of the word problems for these first order linear differential equations, but this one has a special place in my heart. So we're looking at circuits here, RL circuits to be specific. So R stands for the resistance, L stands for the inductance. So to jump into these RL circuits, we're going to be looking at Ohm's law. So if you haven't heard of Ohm's law before, it's not that big of a deal. It's not hard. The voltage is just the resistance times the current. Okay. Now, if you introduce an inductor into there, this changes slightly. So accounting for inductance, we get this. So the inductance times the derivative of the current, di dt, plus the resistance times I is equal to V. I don't know why they changed from a capital I to a lowercase I there, but they just do. But here we go. So this is now kind of the updated Ohm's law whenever you have inductance into play. And what we're going to do is we're going to solve this because this is a first order linear differential equation. So first thing we need to do is we need to get the derivative di dt by itself. So we're going to divide everything by L. So di dt is by itself now, plus R over L times I, and that's going to be equal to V over L. Keep in mind that the R, the V, and the L are just constants. They are not functions of t. Okay, so now is going to be finding our integrating factor. Remember, the integrating factor we get by doing e to the integral of p, where this time p is R over L dt. But those are just constants. So all we're going to do is we're just going to leave the constant alone and then throw a t on there. So this is going to be my integrating factor, e to the R over LT. Then we're going to multiply both sides by my integrating factor and then rewrite the left-hand side as the derivative ddt of my integrating factor, e to the R over LT, times what was y, but now y is going to be the I, the current. All right, and that's going to be equal to the right-hand side, which was V over L, times this integrating factor. Okay. Next thing we want to do is we want to integrate both sides. When we integrate the left-hand side, it just cancels out that derivative. When I integrate the right-hand side, so V over L is a constant, you can pull that out, but then we're going to do the antiderivative of e to the R over LT. Anytime you're doing the antiderivative of an e to an exponent, you're going to take the reciprocal of the constant out and then just leave it alone. So we're still going to have that V over L out in front, but that's going to be multiplied by the reciprocal L over R, and then we're going to leave an e to the R over LT by itself. Don't forget the plus C. Okay, you may see here that these L's cancel out. Oops. All right, so we'll just rewrite this real quick. We still have the left-hand side, which I'm leaving alone. These have now canceled to be a V over R, e to the R over LT plus C. The last step is going to be dividing both sides by this e to the R over LT. So we're going to have the I on the left-hand side by itself, and it is a function of t. Here, it cancels, so we're just going to get that constant V over R. Plus here, we're going to have that constant, and then we're going to have e to the negative R over LT. That's what happened when we divided it over to the right-hand side. Okay, we can find the constant using initial conditions. So initially, anytime you have any kind of a circuit, at time 0, the current is at 0. Usually at time 0 is when you turn on the circuit, so you can see how it behaves. All right, so if I plug this in, initially my I is 0. I still have this constant V over R plus C. This is going to be e to the 0, so just 1. In other words, I get C is negative V over R. Okay, so I of t is V over R minus V over R e to the negative R over LT. Good. So This you may need for a homework question, so make sure you have this written down. But I want to kind of talk through the physics of what we just solved for and how a circuit works. So if you think about a circuit, which is, it's just a wire, basically. So this wire is going to have the voltage from the battery, it's going to have the resistor, and then it's going to have the inductor. How do you do inductors? I think inductors are like curly things. So when you turn the circuit on from the battery, normally, if there was not an inductor, everything would just get a current pretty much instantaneously. But because of this inductor, what happens is that the current takes a little bit of time for it to get going. That's what this term is doing here. As t increases, this term eventually goes to 0. And you can see that if you take the limit as t goes to infinity. So as t goes to infinity of this thing up top here, this term is just going to go to 0, which means that you're going to get I of t becomes v over r. And that should look familiar because if you multiply the r over to the other side, we get this. All right? And remember, this was just initially Ohm's law. So when you have an inductor, it still reaches Ohm's law. It just may take time for it to get there. In other words, an inductor slows down the current so it doesn't build up to the voltage right away. Okay, great. So there's just one example of a first order linear differential equation word problem. We're going to see some more and some more difficult ones here in section 3.